Thank you all for coming. My name is Marco Cusumano-Towner, and I work at MIT in the Probabilistic Computing project. So today I'm going to be talking to you about some new programming constructs for probabilistic AI that we've been developing in our group. So suppose you're given some data, like the image on the left, and you're asked to explain it. One explanation is that this is an image of a coffee mug, but there are lots of other explanations you could give at different levels of detail. For example, you could say that this mug is being viewed from the top. So on the right, the red icon shows the viewpoint of the camera relative to the mug. And this more detailed explanation could be a lot more useful than just saying that it's a mug. For example, if we're a robot, we could plan the sequence of grasping motions we need to do in order to grasp the handle. Now, we could also give other explanations. For example, we could say it's an empty mug, or we could say it's a ceramic mug or a white mug. And there are lots of different ways of explaining this image. But for now, I'm going to suppose that we're most interested in the 3D geometry of the mug and its 3D orientation relative to the viewer. So here's another image of the same mug. So what's the 3D orientation this time? Well, in this case, there's two plausible explanations instead of one. It's definitely being viewed from the side, and the handle is visible, but it could either be standing upright or it could be upside down. And both situations would have resulted in the observed image on the left. So a key feature of human common sense reasoning and probabilistic reasoning is the ability to consider multiple plausible explanations for the data. And in other words, we can be uncertain about things. And uncertainty is going to be a key recurring theme in this talk. So here's one more image of this mug. How would we explain this one? Well, here we probably have even more uncertainty. So like in the previous image, this mug could either be right side up or upside down. But because the handle is blocked, we don't exactly know what angle the mug is at this time. So there's a continuum of different possibilities. So if we didn't assume this was a mug beforehand, actually, there's even more explanations we could give. For example, maybe it's some sort of hollow cylinder-shaped object. Or maybe it's just a cup without a handle. Or maybe it's a solid cylinder of some sort. So the set of possible explanations that we're willing to consider is one of the key types of assumptions that we bring to the problem. And we might also assume that some types of objects are more likely than others, right? So maybe hollow cylinders and strange solid cylinders are less likely in your environment than mugs and cups. So if you see this image, maybe you're more likely to think it's a mug or a cup than a strange hollow cylinder. So these are all examples of probabilistic inference, which we can think of as generating plausible explanations of observed data. So now I'm going to show you another example. Suppose we're in some environment that contains 3 trees and a walled enclosure with a doorway in it. Now, suppose we see a person moving around in this environment. So on the right, each blue X is going to be the location of the person at some time point. So here they're starting at the bottom left at 0 seconds. And after 1 second, they moved up a little bit. And after 10 seconds, they're located here next to the wall. So we want to explain this observed data. So we have to make some assumptions. So first, we're going to assume that they're trying to go somewhere, and that the place they're trying to go is somewhere in this environment. So we can also suppose that they know the environment pretty well, so they're able to plan an efficient route before they start walking. So then the person's destination and their planned route is going to be our explanation. So our question now is, well, where in the environment is this person trying to go? So here are going to be a few possible explanations. They could just be going right where they look like they're headed. So the red dot is their destination and the gray line is their route. They could be going a little further. That's also a good explanation. Or they could be going inside this enclosure. That also makes sense. And they could be going anywhere inside the enclosure, really. Or they could be going across to the other side of this area. So what makes these destinations more plausible or more reasonable than the other points like this one? Well, it's based on our assumption that the person is trying to be pretty efficient in their walking. So we're going to judge circuitous routes like this one to be less likely. So the image on the right now shows an aggregation of all these possible destinations that could explain this data. And again, this is an example of uncertainty. We can't be exactly sure where they're going, but we think that some areas are more likely than others. So lots of other problems can be framed this way. So for example, if we see a sentence, I see a man with a telescope, there's two possible meanings at least. One could be using a telescope, I see a man, or I see a man who has a telescope. And these correspond to two different parse trees for the sentence. And we can also use probabilistic inference for more standard statistical problems, like interpreting some time series data. So here we see some data on the left, and we might say, well, I think this is a sinusoidal oscillation with some fixed period, and there's also a superlinear trend, and maybe there's some pattern going on in the troughs of this sinusoid, but I can't be 100% sure that that's real. It could just be some noise. So in each of these examples, there's some data, and then there are assumptions that we're going to bring to the problem. And one of the key assumptions is the type of explanations we're willing to consider in the first place. And once we've done this inference process and come up with our explanations, those may be of intrinsic interest. For example, like I said, we can use the orientation of the mug to plan a grasp. But these explanations can also be useful indirectly because they allow us to make more accurate predictions of future data. So on the left, if we've inferred their destination, maybe we can actually predict their future motion. In the middle, if we've figured out what the patterns are underlying this data, maybe we can actually make forecasts. And on the right, if we figured out how the mug is oriented in 3D space, we can predict the image we would see if we moved our camera up a little bit. So to solve problems like this, we're going to use probabilistic programming, which is a relatively new programming paradigm and associated set of software tools. And this paradigm draws on Bayesian probabilistic inference techniques, which have been one of the core computational tools for solving problems in lots of areas for years, including natural sciences, like astrophysics, ecology, and genetics, and lots of technology areas, including robotics, genomics, and natural language processing. And these also have been one of the primary modeling techniques for understanding human cognition computationally. So although Bayesian probabilistic inference is a very powerful tool, it's been notoriously difficult to use because it requires a lot of specialized knowledge of probability theory and numerical programming. So one of the goals of the probabilistic computing project and probabilistic programming as a field as a whole is to make Bayesian probabilistic inference techniques a lot more usable and accessible to a broader audience by developing new software tools and new abstractions that hide some of this complexity from the user. So here's one key idea in this new paradigm. So in traditional approaches to Bayesian inference, the assumptions are expressed in some mathematical notation, maybe in the user's head or on some pen and paper, and then they derive a custom algorithm for this particular problem they're trying to solve, and then they implement that algorithm in C or R or MATLAB. In our probabilistic programming paradigm, we're going to declare our prior assumptions explicitly by writing code, and that code is going to be a simulator that generates all the situations that we're able to possibly imagine before we see any data. Then we're going to write inference procedures and we're going to use, with the help of probabilistic programming systems, and I'll show Gen is one probabilistic programming system we're going to use in this talk. And these systems provide tools for analyzing the simulator code and doing various different types of execution of that code. So let's see an example. So this is the inference problem we saw before, and we're trying to figure out where this person is going. So our first task is to write a simple stochastic simulator for a virtual world and a virtual person who's going to be walking around in this world. So I'm going to write this simulator in Julia. So what are all our assumptions? Well, the first assumption is that the environment or the scene is some fixed thing and that we know it. So we're going to assume there are 3 trees and an enclosure. Then we assume we know where the person is starting. So in this case, they're starting in the lower left-hand corner, represented as a black dot. Now we're going to simulate the person's destination. But the destination is something we don't actually know, so it wouldn't make sense to pick any deterministic value. So to express the fact we don't know something, we're going to use randomness. And we're going to pick a random point somewhere in this scene to be the destination, and that's in red. So each time we run this simulator, we're going to get a different destination. Now we're going to simulate the route that the person is going to take to their destination. And remember, our assumption was that the person is going to take efficient routes. So we're going to use a route planning algorithm to generate this route. And this function plan route takes the scene the start point and the destination and generates a pretty efficient route that avoids obstacles. So the routes we get are just a sequence of straight line segments in this case. And next, we're going to simulate the actual location of the person over time, and that's going to be the blue x's. So we could have just simulated points along this route by just walking along the line, and that would give us these orange x's. However, no one really walks in exactly straight lines. And we don't want to assume anything about how a particular person walks. That would be an unreasonable assumption. So again, we're going to use randomness to express the fact that we don't know something. And here we're going to add random noise to each of these orange x's to get these blue x's, which are the actual person's location. And finally, we're going to return this simulated virtual world, which includes the scene, the route, and the start and destination. So there's a bunch of other assumptions in this code I didn't mention, and it can be fun to look through code like this to find what the assumptions are. But one pretty easy one to find is that the speed is fixed. So that's not necessarily reasonable, and to relax it, I could make that random too. Okay, so if I run that simulator, each run generates a different world, right? And here I'm showing 8 worlds produced by running the simulator 8 times. So sometimes the destination is close and the person can just walk in a straight line, other times they have to go around the enclosure. And sometimes they're headed into the enclosure, but we didn't happen to get one of those simulations here. Okay, so we've expressed our assumptions in the form of a simulator, a stochastic simulator. So now what procedure can we use to do inference that uses that simulator? Well, the one I'm going to show you is not very efficient, and later in the talk I'll talk more about how to make these things more efficient. So what can we do with the simulator? Well, the most obvious thing we can do is run it. So basically our procedure initially is going to be to run the simulator over and over again until we get a virtual world where the virtual data in that world is similar to the observed data in our world. And then we're going to return that virtual world as an explanation. So here's the data, and on the right is our first simulated world. So this has the person walking right, but the observed data has the person walking up. So the data don't match, so we're going to reject that as an explanation. We might get this simulation run. This is a little better, but the data still doesn't look quite like the real data, so we're going to reject this one too. So eventually we might get a run like this, where the person's headed into the box, and here the real data and the virtual data are kind of similar, so we're going to say, okay, this could be an explanation for what we saw. And here we get another one that we reject. And here we're going to accept this one, because again, the data are pretty similar. And you might accept this one as well. So if we automated this process, we could run this thing over and over again and basically accept all these explanations for which the data are similar. And here I'm showing the destinations being persistent if they result in if they are a good explanation. And this is basically the inferences that we get at the end. So again, the person's probably headed into the enclosure, maybe above the enclosure, but probably not going to the bottom of the map or the bottom of the scene. So if we run the same algorithm on a different data set, we're going to get different inferences. So here we've inferred that the person is probably headed to the right side of the scene. Maybe they're going into the enclosure, but probably with less probability than for the other data. So here's the pseudocode for that procedure. Again, it works by simulating a random world until it finds one that explains the data, and then it just returns that world. So also, we had to write this explains data procedure somehow, and I'll come back to that later. And also, this procedure, each time we call this, it generates one explanation. So we're going to call it over and over again to get more explanations. And this procedure is using 2 types of information. So first, it's using our assumptions, and that takes the form of running the simulator. And the second type of information it's using is the data, and that is in the form of this check that happens here. Okay, and this principal combination of these 2 sources of information is one of the key ideas in probabilistic inference. So we could also apply that procedure to this, to infer the 3D orientation of this mug. So like before, we're going to start by writing a stochastic simulator. So first, we're going to assume this is a mug. We could relax that assumption, but for now, we're going to say that's given. So to express that we know it's a mug, we're going to actually load a 3D mesh model of a mug. And we don't know the mug's orientation, so we're going to make that random. And we can express an orientation using 3 angles, roll, pitch, and yaw. And we're just going to sample those angles at random. So on the right, I'm visualizing a random virtual world. Next, the step in our simulation is going to be to render an image of what that cup would look like from that particular perspective. And we can use, for example, OpenGL to do that. So we might get the image shown on the right. And finally, we return this virtual world, which has the angles as well as this resulting image. Now, if we did this over and over again, we'd get a bunch of different virtual worlds. So we can run our procedure again for inference. So given the data on the left, we're just going to simulate a bunch of worlds until we get one where the simulated or rendered image looks like the real image. So that one doesn't look like it. Neither does that one, nor that one. Eventually, we will get one that looks close. And here we find out that, okay, this mug is upright and the handle is at a particular angle. Now, if we kept on running it, eventually we would also sample this explanation, and we'd also say, well, this is a valid explanation of the data, so let's accept this too. So if we did this over and over again and aggregated these results, basically we'd get 2 types of explanations that we accept. About half of them would be these upright mugs, and half of them would be these facing down mugs. So there's one assumption that we might want to bake in. So we know that mugs maybe are more often facing upright. So how could we give that knowledge to our system? How could we encode that assumption? Well, because it's an assumption, we're going to go back to our simulator. So the yaw and pitch angles, if those are 0, then we get an upright mug. So we're going to actually encode the information that this mug is usually upright, the mugs are usually upright, by biasing the sampling process for how we generate these random angles. So now we're going to more likely generate angles near 0 degrees for these 2, but we're still going to be able to generate a bunch of other angles too, but they're just going to be less likely. So now if we run our simulator over and over again, we get an appreciable number of simulations that have upright mugs in them. So if you take that new simulator, plug that into our procedure for inference, we're going to get different inferences. So now a greater fraction of the accepted explanations are going to be upright mugs. So you might be wondering a couple things. One, this procedure is pretty inefficient. So as our worlds become more complex, the probability that we generate a virtual world where the data matches the real data is pretty tiny. So that's basically guess and check, right? And the rest of the talk will be about using new constructs to improve efficiency. And you also might be wondering, well, how do you get realistic simulators, right? These can be pretty complicated. So one broad answer is that they don't need to be realistic as long as we can admit our ignorance by adding sufficient randomness into them. Now, a second idea is that also because these are simulators written in code, hopefully it becomes easier to elicit domain expert help to actually express these assumptions formally, as opposed to if you had to, for example, write down a bunch of probability distributions expressing your assumptions. And then finally, we can actually learn pieces of the model or the pieces of our simulator from data if we need to. So before I move on to the meat of the talk, I'm going to talk briefly about the role of randomness in simulators again. So this is our simulator for the person moving around in the scene. And again, the first randomness was the destination, right? So we have to be able to consider all possible destinations. It turns out that if we fix the destination and the start point, we actually get a lot of different possible routes. So our route planner is also random. So sometimes it goes around the left, sometimes it goes around the right. And this randomness is important and intentional because real people don't always walk the most efficient route either. So, and finally, our last piece of randomness was this random noise we added to the actual person's location. So these are all possible virtual worlds here that have the same fixed route. So in all those cases, the randomness is expressing things we don't know. But there's an interesting side effect of using randomness in our simulators. And it's that it allows us to consider pretty weird and unusual worlds as technically possible. So these are all pretty reasonable worlds. The person's location is pretty close to their route that they were walking along. Now, here are some other worlds. These are also possible, but now the person's location is a little more dispersed. It's further away from their route. So these are still technically possible, and we don't want to rule them out, but they're less likely. So now I'm showing a sequence of worlds where the person's location is gradually being pulled away from their route. And as we pull these locations further and further, these worlds become less and less likely. So they make a lot less sense, right? Why is the person walking when their route was over here? But they're all technically possible still, according to our assumptions. So we're going to call this simulator, or this property of simulators, the stretchiness of a simulator. And each of these worlds is stretching the simulator to a different degree. So as we stretch it more and more, basically these worlds are becoming more unusual and strange, and the simulator is going to be pulling back with greater and greater force because it really wants to produce typical worlds. So this stretchiness in our simulator, it turns out, is going to help us write more efficient inference procedures. Okay, so how can we do inference more efficiently while still using simulators to express our assumptions? Well, we're going to need more capabilities besides just being able to run a simulator. So for example, we would like a way of measuring quantitatively how well a given simulated world explains the data, instead of having to define a very restrictive filter that's basically going to reject basically most of our simulations. So that the first one is going to be quantifying the degree of match. And we also want to iteratively improve a simulated world in order to make it match the data better. That way we can start out with a world that doesn't match, then improve it gradually instead of having to start from scratch each time. So versions of the constructs I'm going to present are implemented in the Gen probabilistic programming system, which is embedded in Julia. And when solving an inference problem in Gen, the user first begins by writing a stochastic simulator to express their assumptions. So Gen simulators are like Julia functions, but they have additional runtime capabilities beyond regular execution, and they have some additional syntax. So we start off with the Julia simulator that we saw before. And to make this into a Gen simulator, we add this Gen annotation in front to make it a Gen function. And also, we add annotations in the code for some of the random choices the simulator is making. And we're using this @trace expression, which is a Gen expression. And we're assigning some of these random choices with a unique ID, shown in red. And so these destination IDs are dest x, dest y. There's IDs for the actual location, which are these tuples, location 1, location 2, and so on. So the full set of IDs that we get for this simulator is shown on the right in red. And I'm calling this keyword trace because when Gen executes this code, it's going to record the values of all these random choices into a sort of execution trace, which is in part a key value store mapping these IDs to the random values they took in a particular run. And we're actually going to use the execution trace of the simulator to represent our virtual world. And because Gen is assembling this data structure for us, we actually don't need to return this virtual world. So I'm just going to delete that line. So again, the execution traces of these Gen functions are going to be virtual worlds. And these are going to be the primary data structure that our inference procedures are going to manipulate. And we're going to manipulate those using these IDs as handles to refer to specific random choices that the simulator made to control its execution in different ways. Okay, so now we're ready for our first new programming construct. So our first procedure for inference had two issues, right? One was that most simulated worlds didn't match the data, so it would take a long time before it returned anything. And the second was that the user needed to define a condition to explain the data, right? There's this mysterious explain data function. So the first construct, which is completing a partial trace of a Gen function, addresses both of these issues. So this function I'm calling complete trace, and it takes a simulator and a partial trace. And the partial trace is just going to contain the parts of the world that we've actually observed. So in this case, the only thing we observed is the location, so we're passing in this partial specification of a world. And we're using the IDs to refer to those specific pieces of data. And what complete trace does is it fills in the rest of the world by selectively running parts of the simulator. So here we'd have to run all the blue code, basically, and we wouldn't need to run this orange line because that line generated the person's observed walking location, which we were given. So because this world that we get is constructed by fusing together two different components, some of these resulting worlds are not going to make a lot of sense. So here's a world where the steps the person takes is kind of a little bit off the path, or off the route, right? So it kind of makes sense, but not that much. But we could also have gotten this world as the output from complete trace. So here, it doesn't make any sense. The person's route was going to the right, but they were walking up. So, and the length of these pink lines indicates how much this is sort of stretching our simulator, how much tension there is in the simulator to accept this. Now, crucially, this function complete trace also returns a score, which quantifies basically how well this world explains the data. And this score quantifies like how much the world is stretching the simulator, basically. So now we can, instead of throwing away all these simulations, we can still use them because now we have a quantitative number for how well they match. And Gen is computing this score automatically, and therefore there's no need for some heuristic to decide whether the simulated data matches the real data or not. This is all determined uniquely by the simulator code. Okay, so now here's a new inference procedure we can write using complete trace. It takes in the data and some computation budget n. And it basically is going to complete n traces, or n virtual worlds, all starting with the data as the partial trace. And it stores the traces and the scores. Then it randomly chooses one of these completed worlds to return based on these scores. So a world with a higher score is going to be returned with higher probability than a world with a lower score. So we're going to be most likely to return the one in the middle. We might also return the one on the left with some probability. So unlike our original procedure, right, this procedure terminates in a fixed and predictable amount of time because we got to set the computation budget. But it's interesting to see when n equals 1, our inferences are actually identical to if we just ran the simulator from scratch. Right? So here we're not taking the data into account at all. And as we increase n, the inferences become more and more close to the mathematically correct definition of Bayesian probabilistic inference. So this procedure is called importance sampling in computational statistics. But with a system like Gen, the user does not need to derive custom equations to compute these scores. And you can implement a generic version of this procedure in just a couple lines of Julia code using Gen. Okay, so that gave us a principled procedure for inference with a predictable running time. So that's some progress, but it's still basically guessing worlds from scratch. So the next construct is going to be about iteratively improving a trace until it better and better explains the data. So this we're going to call improved trace. And that's going to take a simulator, a trace of that simulator, this time it's a complete one, and a part of the world to try to improve, and a computation budget n. And it's going to return a new trace that's hopefully makes more sense, and that stretches the simulator less. So here our initial trace might be on the left. If we decided to improve the x-coordinate of the destination, we might get the new trace on the right. So again, here we've kept the y-coordinate fixed, and we just can shift this x-coordinate over a little bit, and we get one that makes more sense. Now, this procedure isn't deterministic because there's lots of other ways to shift x and still get equally valid explanations. So we could have moved x into the box. Now, here's another example. Suppose we started with this trace here, where the person's route is going to the right. If we ran improve on the y-coordinate, we would be able to move this up and get an area on the upper right, which makes a lot more sense. So we can use this improved trace construct to write a third inference procedure. And this one's pretty different than the other one. This one starts with basically a random world, sort of a really world that doesn't make much sense, returned by a complete trace. And then it iteratively improves the x and y coordinates of the destination. So first, we're going to move the x-coordinate left. That makes the world a little better. Then we're going to move the y-coordinate up. And now we basically have decent explanations. So if we keep on running this for loop over and over again, we actually start exploring a space of different worlds that are all good explanations. So improved trace basically has two roles. The first one is to get you from a crazy world that doesn't make any sense into one that's a good explanation, but you can also use it to explore the space of good explanations. So this approach to Bayesian inference is known as Markov chain Monte Carlo, or MCMC, and Gen, again, is providing users with tools for implementing MCMC at a pretty high level of abstraction. by automating the data structures and the derivations of the probabilistic equations and numerical calculations and so on. Okay, so now we've achieved some level of customization to the problem, but there's lots of things that this framework still doesn't let us do. So what if we, for example, have some heuristic that solves a related problem, but that problem isn't really Bayesian inference or probabilistic inference, or it's not the same problem? So how do we use that with this simulator-based approach? So let's see a toy example. So suppose we're trying to solve this problem on the left. So we're trying to infer the 3D orientation of this mug. Suppose someone has given you some code which solves this problem for cylinders, because cylinders are a pretty common 3D geometric primitive, right? So that seems like a related task since mugs are kind of like cylinders. And suppose this off-the-shelf code was actually robust enough to work on this example. So it accurately fits a cylinder to this image, and it returns the 3D orientation of the cylinder. So that would partially solve the problem. But the cylinder detector doesn't know about handles, right? So it can't ever figure out what the angle of the mug is around its axis. And it also doesn't know that there's an up or down orientation to these mugs. So we can turn that code into something that solves our problem, or at least has the right type signature, by randomly picking the orientation around the axis and randomly flipping the mug upside down. But we're going to keep the axis fixed to what the heuristic told us we should. So if we ran that, including the random pieces, we'd get results that look something like this. So the top row, again, contains all these upward-facing mugs, but there's all these possible rotations of the handle. And the bottom row contains the bottom-facing mugs with all the possible rotations of the handle also. Now remember, the correct inference was to put 90% probability on upward-facing mugs with the handle at a specific angle. So our heuristic is wrong in two ways. So first, it's not taking into account the existence of the handle, right, because it doesn't know about handles. But also, it's not taking into account our prior assumption that upright mugs were more likely than downward-facing mugs. So we could try to mess with our heuristic and encode, get it basically to do that, but that could end up being pretty brittle. And our simulator already has the information we need encoded in it to solve both of these problems. So how can we combine the simulator and the heuristic? Well, there's lots of different ways to do that. I'm going to show one. And we're going to use a variant of this complete trace construct that we saw before. This variant takes an extra argument, which is going to be the heuristic. And it analyzes the simulator code and the heuristic code together to make sure that they're compatible first. Then it runs the heuristic and completes the trace like we saw before. So that, again, the heuristic is being used to fill in this world instead of the simulator. Now, we're going to return a score like we did before, and this score is going to quantify how well the world explains the observed data. And in this case, for example, this would allow us to reject the third image, the third hypothesis here. So that solves, the first problem because we can discard those worlds with the handle at the wrong angle. But this isn't taking into account our assumption about upright and downward mugs. So this variant of complete trace actually has a correction term that it adds to the score, which accounts for the fact that the assumptions of the heuristic were used to generate the explanation instead of the assumptions of the simulator. So it's going to upweight worlds where it's facing up and downweight ones where it's facing down. And then we can plug this into another inference procedure, which is basically just like the infer2 procedure, but now it uses the heuristic. And if we run this with enough computation budget, we should get the right answer too. So now let's see qualitatively how this heuristic is helping us. So first, let's consider this inference procedure we saw before, infer2, that did not use the heuristic. So with a computation budget of 1, n equals 1, we get pretty low accuracy. In fact, it's just behaving like the simulator itself, so it's just reflecting our prior assumptions. So these are just all the random orientations we could imagine. Again, as we increase n, even without the heuristic, as we increase n, we approach the optimal Bayesian inference. And in blue, I'm showing the behavior of our new procedure infer4, which uses the heuristic. So when this procedure is run with n equals 1, it actually behaves just like the heuristic. So hopefully the heuristic is more accurate than our prior assumptions because it's taking the data into account, but it also might be wrong in all sorts of ways, like we saw. But as we increase the computation budget on this new procedure, we actually also approach the same inferences as we did originally. So we're going to get the correct Bayesian inference. And we're going to be able to do that with less computation cost. Okay, so our final construct is going to allow us to learn good heuristics in a principled way automatically using training data generated by the simulator. And in particular, this is going to allow us to use things like deep neural networks in our heuristics. So here's an example. Suppose we have a simulator for silhouettes of a human body on the right. And the way the simulator works is first generating some joint angles, then using some computer graphics techniques to generate a mesh, then rendering that into the silhouette image on the right. And some of the random poses this can generate are shown on the bottom. Now, we can generate synthetic examples by running the simulator over and over again, and then train a deep neural network to predict the joint angles from the silhouette. And Gen is going to give us the loss function we need automatically to do this training in a principled way. So if we just run the resulting trained heuristic based on the neural network, we'll get something that kind of works, but in this case, it has lingering uncertainty about the elbow angle. If we add this heuristic into our infer-for inference procedure, we can actually resolve that ambiguity. And the way that works is we're actually rendering each of these poses proposed by the neural network through OpenGL and checking whether the resulting data actually matches the observed data. So this is one example of how deep learning and the simulator approach to inference are complementary. So I just gave the perspective from simulator-based inference, where we're using deep learning to make it more efficient by amortizing the cost of training the deep neural network across many problem instances or many inference problems. But we can also take the perspective of someone who works in deep learning. And so recently in deep learning, it's become more popular to use simulated or synthetic data for domains where it's really hard to achieve lots of hand-labeled data. But here we're actually using simulators at inference time also, and not just offline for training data. And the reason why that's less done is because to do that, you really need to write your simulators in a language like this with these new programming constructs. And with those new constructs, in languages like Gen, we're able to improve the robustness of deep learning. So some ongoing projects we have that are using this approach and using Gen include 3D scene understanding, audio scene analysis, causal inference, and collaborators are also applying Gen to data science tasks like probabilistic cleaning and imputation for data tables. And Alex Lev is actually giving a talk on that tomorrow that I recommend you attend. That's all. Thank you.
So your traces ignore a lot of physics. For example, your example with the room. You obviously exploit the walls. You know that the walls are part of the path. And these are expensive things to build. Why aren't you incorporating physics in your trace computation? Because your traces clearly cross the walls, and that looked like an unphysical situation in your expansion. So that's a trivial thing that you could, with a little bit of physics, cut those out of your probabilistic model and increase the value of your trace system, I presume. I'm just watching this the first time.
Yeah.
Is that a fair assessment?
So the question is, it's pretty obvious that we can use physics to avoid physically impossible worlds. Wouldn't you want to make your simulator more accurate, more physically realistic? So yeah, I think that's this question of, you can always make your simulators more realistic. That does make them more complex. So one degree is a complexity of implementation versus what it's giving you in terms of accuracy. So I agree that, yeah, you get more accurate inferences, but it might be more complex to implement and the running time would be higher. So that's sort of the trade-off. That's, I think, the primary trade-off, is we want to provide a design space where you can implement pretty simple things that are kind of stupid, or kind of dumb, right? But they're really easy to implement, and maybe they're dumb in ways that aren't catastrophic. So if we implement a simulator that is ignorant of physical laws, but we add enough randomness to express that, then it's just going to be uncertain, too uncertain. right? It's not going to necessarily be overconfident. That's, I think, a sort of graceful decay in performance direction. So that's, yeah, thanks. Hi.
When you were building the trace score and you were rejecting worlds that were like aligned with the starting cap, how did you took that score to make those determinations on which world you rejected?
Yeah, so for that, I was using the sum of the distances between the data points that corresponded. So that I was implementing that in the very beginning as part of our heuristic procedure for checking whether the data matches. But the actual score, it's not exactly doing that, but actually it turns out, so it basically is computing a probability of how probable is this virtual data, or how probable is the real data given the rest of the trace. And it turns out that that probability is basically proportional, or the log probability is proportional to that sum of distances in that case. So it's basically, the intuition is the same. But the thing is that the system is computing that for us using the randomness and the probabilistic semantics of the simulator instead of us having to derive that as a manual heuristic. Yes?
Just to come to your question, how do you decide the threshold what is a local route planner?
Yeah. So the question is, how do you decide a threshold on, was it on what is a good explanation of data or the, okay. So I think, right, in the beginning, you could set an arbitrary threshold in the first part of the talk. The second part of the talk says that basically that score, there's no threshold, there's no hard threshold that is involved. So really, that quantitative metric of how close it is being determined uniquely by the simulator. So you can modulate this quantity by changing the randomness in your simulator. So for example, if you had a simulator where I made these locations random, very random, right? Like the blue X's would be all over the place, then I would be more willing to accept worlds where the blue X's don't match the route. So it's basically, and that's an important degree of freedom, which is in part modulating the trade-off between computational difficulty of this problem and how confident you can be.
I think the question is sort of asking, like, once you have these scores, do you need to set a threshold, or like how do you avoid setting a threshold? And that's this important sampling.
Right. So that procedure is void setting a threshold. Exactly. Yeah. And it does have a computation budget, right? So the more you run it, the results do change, but. Yes.
You've shown some fairly complex examples of scoring functions, like a cup. I don't know how you compare the simulated version to the ideal version. How do you deal with short discontinuities that come from the scoring function? So for the cup, for example, if you rotated it, then it would like blow out because of the highlight.
Right.
2 degrees more, you don't have the highlight, and suddenly the score goes back.
Yeah, exactly. So particularly for graphics, that's a really hard problem. And
Joint position, right? Like it could be rotated 180.
yeah, so one thing we can do is, and we're doing this in some of our other projects, instead of using the literal image, instead of basically trying to simulate a photorealistic image, right, which is going to be super complicated, there's all these things you can't take into account necessarily, we're going to only simulate some simplified version of the data. And then, so for an example is, if we can go from our real image to something that just is a depth image, right? Then we can simulate realistic depth images a lot more than we can simulate realistic photos, right? So basically, we can always try to move from this original data space into some simplified form where we've applied some pre-processing and tried to take away some of these nuisance variables, like the lighting, for example. So another example that people have applied for images is basically running an edge detector on the image. Because edges are going to be, the edge image is a little more invariant to some of these things than the actual image itself in the original image, right?
My question, which is great, so how much do you find yourself doing this kind of refinement? Because while exploring it, you find these areas, because they're not necessarily easy to find, and then you run it on like big inference questions, and suddenly you're like, I totally missed this
Right. So I think one thing that we're trying to do is build reusable components. So graphics rendering, right, is a reusable piece. We can use that in many different projects. So if we can figure out how to do it for graphics, then it's a reusable code. And this also is one of the reasons why we want to use code to represent our simulators, right? Because we can use code, we can just make function calls to a graphics library, right? So we can reuse pieces. So basically figuring this out for images is a research problem that is continuing to be worked on. Yeah. Yes.
Is the underlying philosophy of using this language is most of the use cases going to be in the computer vision?
So that's what I happen to be focused on right now. I think, yeah, basically I think that the underlying technique can be applied to all sorts of other areas too.
Yeah, one thing I find a little different is because I had a little bit robotics background where it seems to be like, we assume the world to be deterministic, and we assume that we now have the whole knowledge of the world, which is like in robotics, there's like, you do SLAM, like simultaneously mapping, you make a step and then you sense and then you go another step, and then sometimes you also do continuously movement instead of like stepwise movement. Seems to be this use case of this gen language seems to be maybe like more catered to computer vision instead of some other fields such as robotics.
Yeah, we can. I think that's a really interesting question. I would like to talk more about that actually offline, but it sounds really complicated. We should get into it. Yes.
Do you ever consider refining the amount of randomness, like using clustering algorithms or something like compare the uniqueness of the random situation generated to also increase that efficiency, like clustering algorithms or something like that?
Yeah. So the question is, do we use clustering algorithms to determine the amount of randomness to use? So I think one thing we can do is we can try to learn the amount of randomness that we need.
But just don't retest the same randomly. Like if it generates the same point again, it's.
Oh, I see. Okay.
You've already simulated that, right? So you can reject it earlier.
Yeah, that's interesting. Yeah, so there are like adaptive versions of these techniques where instead of just like for the improved world for loop, right, you can make these things adaptive so they have some memory. So yeah, there's like a whole space of elaborate procedures there. And the idea is that systems like this, because these are pretty low-level constructs, you can still explore that space of interesting things. Okay, I think I'll take the rest offline. Thanks.